first, let me just review the major ideas that we need to know for the exam number 1, right? So, of course, key formulas, right, key concepts. Okay, so let me start with electric field, right? So we introduced electric field in that way, right? So if you have some charged system, it produces the electric aura, and of course we can describe that aura using first either electric field, so you position probe charge, calculate or measure the force acting on the probe charge, and divide it by the value of the probe charge, right? So that's how we introduce electric field. Then next situation, let's say you have area filled with okay, some area which is exposed to the electric field E, and let's say charge flies through that or exposed to that field. Of course, that charge is going to interact with that field. So the question is, how can we describe that interaction? Of course, any interactions are described by the force. So we introduce force, electric force, charge, which is exposed to the field, times the value of the electric field. So it's one of the universal formulas which forms the foundation of electricity and magnetism. So then, but at the same time, that electrical aura can be described using scalar quantity, because electric field was a vector quantity, right? So we introduce electric potential. So in a similar way, right? So quantity which describes interactions divided by the value of the probe charge. In this case, potential energy divided by the value of the probe charge. So that's how we introduce electric field. You see similarities, right? Almost, okay, very, very similar expressions. And then, of course, a similar situation. What if you have some area exposed to that electrical aura, which we describe using the electric potential? So the same question. So how can we calculate potential energy of interactions of that charge with that electrical aura? So we can just take the value of the charge and multiply by the electric potential. So that's how we can find the electric potential energy. Again, it's the energy of interactions. Okay, so pretty much at the very beginning, I'm mixing the beginning of the semester and the recent material. Just every time I keep changing, keep moving material. So now I decided to try this. So then, 2-point charges, now at the very beginning of the semester, right? So if you have 2-point charges, of course, we introduce Coulomb's law. Everyone knows that, right? So it's a force describing interactions of these 2-point charges. But then, since this electric force is a conservative force, we introduce potential energy. Potential energy of these interactions, right? So it looks like Coulomb's law, but downstairs we have the first power of R. And again, this is the scalar quantity. And we introduce the electric potential in this way. So as a result, we can introduce electric potential produced by the point charge Q at the distance R from the point charge. So we've been using this formula for the last couple of classes, right? So and again, the beauty of this quantity, it's a scalar. It's so much easier, so much pleasant to work with that. All right, so that's related to the system of point charges, right? You see this line. So now the line which is connected to a capacitor. So if you have a parallel plate capacitor, negative electrode, positive electrode, right? Then, of course, yeah, if you have a charge position inside of the capacitor, of course, we can find the force acting on the charge as QE. Basically, it's just I rewrote this here, right? And at the same time, we can introduce potential energy of interactions between this point charge and a capacitor, or uniform electric field created by the capacitor. And we derive this formula in the lecture: potential energy, QES. And of course, we need to remember S is measured from the negative electrode all the time. So that's how we derive that formula. Right. Charge, of course, can be positive, negative. Electric field, strength. It's basically absolute value of the charge, of the electric field, And, all right, so again, using this general definition of the electric potential, we can also introduce the electric potential inside of a capacitor, right? So it's the value of the electric field times S. Again, S is the distance from the negative electrode, right? Okay, so that's stuff related to a capacitor. And after this, okay, let's just review quickly Gauss's law. Right. So if you have some distribution of charges, it can be any distribution of charges. Then if you pick a closed surface, the keyword closed, it must be a closed surface. Any closed surface your soul desires, you can pick, right? So it's a universal law, right? Then Gauss's law works. If you calculate the total electric flux through that Gaussian surface, this is the electric flux, remember, then it is proportional to the total amount of charge inside of the Gaussian surface, right, and divided by epsilon naught. Right? So we've practiced this Gauss's law enough, right? So I don't think that additional discussions are needed. Of course, I should have mentioned that if a charge outside, we're not counting towards the enclosed charge. Then, of course, a significant part of the Gauss's law is the electric flux. Physical meaning of the electric flux, it's a number of electric field lines crossing a certain surface. In the simplest case, when you have uniform field and flat surface, we can use just a dot product between these two vectors, right? And of course, in the most general situation, like what we have in the Gauss's law, of course, you have to do integration over a surface, right? Which is, of course, it's a calculus 3, which we don't actually integrate this integral. We just justify how we can get the answer. So after that, we applied Gauss's law to get properties of conductors, properties of metals. And keyword in the electrostatic equilibrium, E/static, electrostatic equilibrium, right? So what happens in the electrostatic equilibrium? If you take a piece of a metal, let's say exposed to some external electric field. At the very beginning, inside of the conductor, there will be a mass, right? So of course, electric field will get inside of the conductor. Electrons start running like crazy of course, in the proper directions, and the electrons will keep running and running and running until inside of the conductor they will create an internal electric field, so that superposition of external field and internal field gives us zero net electric field inside of the conductor. So at that moment, when the net electric field inside of the conductor becomes zero, electrons stop running. So after this, we can say that this conductor is in the electrostatic equilibrium. So every time we sort of tacitly assume that every time we will wait for this short period of time, and then we'll wait till conductor reaches this electrostatic equilibrium, and then pretty much all the problems are about conductors in that state, in the state of electrostatic equilibrium. So properties. Conductors have tons of free electrons. It's the major property. The rest can be derived, can be justified, right? So this is the major. And then electric field inside is zero. No matter what's the electric field outside or what's outside, electric field inside will be zero, right? Then if you charge a conductor, charge, it means there's an excess charge. So the excess charge can be only on the exterior surface. We proved that inside of the conductor it's impossible to have excess charge. It doesn't mean that it's impossible to have charge inside. Inside, of course, there are tons of free electrons, but at the same time, there's exactly the same amount of positive charges. So overall, inside, it's electrically neutral inside. So there are no any excess charges. So excess charge can be only on the exterior surface. Then, electric field outside of the conductor, again, in the electrostatic equilibrium, all the time perpendicular to the surface. And the expression for the electric field is eta divided by epsilon naught. What is eta? The surface charge density, because I just mentioned that charge can be only on the surface. So we can only talk about surface charge density, right? Amount of charge per unit area. Right, so that's pretty much the extent of the material, right? So frankly speaking, it's not that much. Before the final exam, we will have more material, right? Significantly more material, right? So exam 1, in terms of the amount of material, is not that bad. It's not that bad. But I know that you're still scared. Of course, it's nature, all right? Everyone is scared, right? It doesn't matter how confident you are. Okay, so Now, just one problem about each of these formulas. Let's just look at different problems related to each of these formulas. But before we start looking at the problems, let's just again review vector algebra very quickly, because yeah, we have tons of vectors everywhere, so we need to have a strong skills of finding components and of the vectors and dealing with vectors. So let me give you a few examples. So let's assume that we have this coordinate system x, y, and let's assume that we have for example vector like this. So let's say it's a vector, you know what, yeah, vector a, right? Completely arbitrary vector a. And let's assume that, for example, this angle is given, angle alpha, right? And just making it up, basically. So I want to find components of this vector a, right? Very often, okay, not very often, but I see students, whenever the vector is away from the origin, they kind of a little bit they start panicking a little bit. Okay, if you don't feel comfortable when the vector is over there, you remember a property of vectors. If you grab the vector, preserve its magnitude and direction, you can position it anywhere you want. For example, you can grab this vector, position it over here, okay? And you will get exactly the same components. Basically, it will be the same vector, right? But in order to practice sort of outside of the away from the origin, so I put the vector over there. Okay, so let's find components. Of course, components, in order to find component, you need to draw these. So component of this vector in the x direction, so x component, right? So this component points in the positive x direction, so the component is positive. Now, how can we write this? So it's a sub x equals, it's basically properties of right triangles, nothing else. It's a hypotenuse, this is adjacent side, that is the opposite side. Since we want to find the opposite side, we need to take a magnitude of a times sine of angle. Sine work with the opposite side, right? A times sine of alpha, right? So what about now a y component? Y component, it's this one, right? And this component, you see, points in the negative y direction. So that component is going to be negative. So let me draw something like this, right? This arrow showing that I'm talking about that. So, of course, this a sub y will be minus, because the component is negative, points in the negative y direction. And hypotenuse, which is a n times cosine of alpha, since this side is adjacent to the given angle, and then of course cosine function, it must be used, right? All right, so these are components of this vector. Now the next one, what about, I don't know, here? And after this we will move to problems. So let's say this is vector b. So how can we find components of this vector b? The same, so we need to project it on the x and y direction. So let's start with the x. So draw a normal line towards the x, right? And this horizontal component, this horizontal vector is the component of this vector b. Okay, which angle is given? Let's say this angle is given beta, right? You see, now I pick this. Again, it depends on the problem which angle is given, but just I pick that vector, right? So x component now points in the negative x direction, so the component is going to be negative, right? So b sub x will be minus, and then since we want to find the side adjacent to the given angle, cosine function, right? So it will be b times cosine of angle beta, right? You have, of course, different people have different sort of like a mnemonic rules how to remember which function to use, cosine or sine, right? I just remember opposite sine, adjacent cosine, right? Sometimes I tell students something silly like this, right? So cos, it's like a cozy adjacent, okay, cozy, a neighbor adjacent, right? So completely silly, stupid, right? But if one student heard this and he liked it, right? So it helped. So you can come up with your own mnemonic rules how to remember those properties of conductors. Okay, so now y component. Y component is this, of course, right? It points in the negative y direction, so this component is going to be negative also. So let me show it like this. So that component will be b sub y minus, because we're not using conventional angle, we use convenient angle, right? So we have to take care of those pluses and minuses manually. So it will be, this side is opposite to the given angle, so sine function must be used. So it will be hypotenuse times sine of the given angle. So b times sine of beta. Okay. So just refresh that. But of course, most of you are quite familiar with properties of right triangles and components. But still, I still see that lots of students struggle, right? Grading the exams and running the classes. Okay, enough of this. And now let's continue reviewing vector algebra, right? It's a problem similar to the problems which we discussed at the very beginning of the semester, where I told you the goal of those problems was to review vector algebra. So this will be, probably I will just write problem number 1, right? And what? We have coordinate system, and let me put here a few point charges. Two are positive, right? So let's say here is 1 point charge. Here is the second point charge. These are positive, right? And the negative one is here. And let me estimate the amount of space I might need. Okay, it should be enough. So, and now let me write. So this is positive plus Q2. So this is plus Q1, it's positive, and this is minus Q3. So 2 positive and 1 negative charge. So we need to find, of course, the question can be about finding the net force acting on any of these charges. For example, on that or this. But the problem asks about finding the net electric force acting on this charge, right? So let me write. So we need, there are no, no, numbers are given. Numbers are given. Okay, let me write them down. So we have Q1 is plus 2 nanocoulombs. Q2 is plus 4 nanocoulombs. Again, guys, if something not clear in terms of handwriting, tell me immediately, right? Right. Okay, I'm just looking at your chat. It's not the amount, it's understanding how to apply it. Okay, no, it will be time consuming. So yeah, it's right now the session is being recorded, right? So I'm trying to record everything. And Q3 equals to minus 5 nanocoulombs, right? Okay, so, and as I said, we need to find F1, basically the net force acting on the charge 1, right? Okay, so it's a very, very similar to the problems which we discussed at the very beginning. And this is the review. Okay, so first, I usually prefer to have a nice drawing, because if you have a nice drawing, chances of making mistakes significantly go down. Right? All right, so let me draw all forces acting on Q1. And again, since we want to find the net force on Q1, of course, all the vectors I will draw over here attached to this charge Q1. So let's start with Q2. Of course, this charge Q2 is going to exert force. These two charges are like charges, positive, of course, force of repulsion. So there will be this force. So which way I label it? F12. F12, right? Indices are self-explanatory, right? Since it's a force between charges 1 and 2, so the force F12. Then, of course, right, let me draw this dashed line, right? And of course, now this charge is going to attract the positive charge. So there will be force of attraction pointing that way. So let me draw it. So this will be F13, right? And so now, of course, if you add them up as vectors, okay, more or less decent parallelogram. So this will be the force F1, which needs to be found. Yeah. Okay, so and now when we see everything in the diagram, so the strategy, like in the problems which we discussed at the very beginning. So first, I want to find the magnitude of this force. 2-point charges, it's a direct application of the Coulomb's law, not big deal. Then we can easily write components. X and Y component, in this case, it's a piece of cake, right? Then we'll do the same with this. We can find the magnitude of this force, again, using directly Coulomb's law. Why I keep dropping it? Right. And then components. Of course, I will introduce one of the angles, and then in order to find components, right? Classical way of addressing a problem like this. Okay, so now let me separate introduction, and now let me start with F12 because it's easier one, right? And again, I'm finding the magnitude, directions I see on the diagram. So if some charges are negative, over here I'm going to use just the absolute value of all charges because I just want to know the strength of those forces. Okay, so it will be K Q1 Q2 and divided by the distance between them. Some geometry is given and I didn't give you geometry. All right, so let me write it down. Let me fix this. So this distance is 3 centimeters. All right, so let's say this is a 3 centimeters and this distance be 4 centimeters. Again, numbers are nice so that we can have calculations will be easier. Calculations will be easier. Right. Okay, so now the distance between 1 and 2, of course, just b squared. B squared, and of course, it must be in meters. Let me emphasize, in meters. Don't forget to convert in meters. Okay, I'm not going to plug numbers. K is known. Charges are given. Again, don't forget about nano. Nano 10 to the power of minus 9, right? Okay, so maybe I will write here underneath to remind you. So it's a 5 times 10 to the power of minus 9 coulombs, nano. Because very often students on the exam ask, so what does it mean M, what does it mean N, what, right? Sooner or later you will get used to this, of course. So if you plug numbers, you will end up with 4.5 times 10 to the power of minus 5 newtons. Again, this is the magnitude, the strength, right? Again, direction is on the figure. Right, now, of course, we can easily write components. F12 x component, since the vector is purely in the x direction, so the whole this strength is in the x direction. So it will be 4.5 times 10 to the power of minus 5 newtons. And of course, F12y will be 0 because here there is no y component of that vector, right? It's purely horizontal. Okay, so let me frame this because I will need this later. Right. So that's F12. Now let's do the same with F13. So first magnitude, F13 equals K. And as I told you, so Q1 and then absolute value of Q3. Q3 is negative, but I see the direction. I will take care of pluses and minuses later again. All right, now I just want to find the magnitude of the force. Right, Q1 times absolute value of Q3 divided by R R13 squared. Whereas R13, it's a distance between the charges involved in this game. So Q3 and Q1. So this is R13. And of course, R13 can be easily found. It's Pythagorean theorem, right? So R13 squared equals to A squared plus B squared. So of course, R13, 3 and 4, of course, is going to give us a hypotenuse of 5 centimeters. Of course, don't forget to convert to meters. So it will be equal 5 times 10 to the power minus 2 meters. Right. So again, you can plug numbers. I will look at my notes. Right. And of course, don't forget to square again. There's some several silly mistakes I've observed in the past, right? Students forget about squaring. Students forget to use nano, right? So just they usually like use 2, 4, and 5. It's a mistake, right? And yeah, of course, conversion to meters. So these are, as far as I remember, like 3 typical mistakes. Of course, when students see that that mistake is that mistake was corrected, of course they will look, oh, damn it, how come that I forgot about that? So be just careful. Most of the stuff you know, you just need to realize when this or that needs to be applied. All right, so yeah, back to the number. So it will be 3.6 times 10 to the power of minus 5 newtons. Right? Again, that's just the length of this vector. Now we need to find components like we've done over here. So now we have to pick the angle which we want to use in order to find components. X component, this one, and the Y component, that one. So I will use the angle this. And I think I label it theta. Yeah. So let's just introduce this angle theta. And of course, we can find the value of this angle, but I will just find cosine and the value of cosine and sine, because that's what we will need to find components. We will need to know cosine of this in order to find x component, and we will need sine of this angle in order to find y component. So let me just write down those numbers. So cosine of theta equals, look at this triangle, this point, that point. You see geometry is given. This is A, this is B, and we just found R13, so 5. Hypotenuse is also found. So we can find cosine function easily. Cosine function, it's a ratio of adjacent versus hypotenuse. Right? Adjacent 4, hypotenuse, this is 5. Right? So it will be B over R13, so it's B is 4, and R13, this hypotenuse is 5. Yeah, 4 over 5. So it's a cosine. Of course, you can calculate angle if you want, but for the next step, this is enough. Right? You will see in a second. And of course, I can find sine function as well. Sine of theta. Again, guys, if you need more explanations, just say something, scream something, right? So it will be, of course, opposite versus hypotenuse. So opposite is A over R13. So it will be 3 over 5, right? So, okay, so that's what we need. And now we can find components like there. So let me show those components. This will be X component, right? And this will be Y component, right? Of vector F13. Right? Okay, so let's find F13 X. X component, you see this blue, it points in the negative X direction. And that minus that minus is not going to appear automatically because we're using convenient angle but not conventional. Conventional angle is measured from the plus X in the counterclockwise direction. So if we use that angle, the minus would appear automatically. But since this angle is more convenient and we use that, we have to take care of the pluses and minuses manually. So I have to put minus in front. Right? Like over here we discussed, right? So it will be, of course, F13 times adjacent side, so we need to use cosine of angle. Cosine of angle, and cosine of angle is here. So we don't have to, you see, we didn't have to calculate angle theta. That's why I just calculated cosine, because that's what I need here. So I can plug it, and F13 is here, and I will just use my notes in order to write down the value of this component. So it will be minus 2.9 times 10 to the power of minus 5, just the force, newtons, electric force, but still it's just a force. And similar for y component, right? Y component, no, not similar. Y component points in the positive y direction, right? In the positive y direction. So of course the component is going to be positive, right? So of course, let me just emphasize that it's a positive component. And again, 1/3 times sine of angle, since this side equals to that side, right? It's basically a rectangle. So this side and that side are the same. So we're talking about this side which is opposite to the given, to the found angle, opposite sine function. So again, if you calculate numbers, plug numbers and calculate, you will end up with 2.1 times 10 to the power of minus 5 newtons, right? Okay, so we've achieved the same for the second vector, right? So I can frame it with green, because now I need to just add these components with that, these components, in order to find the components of the net electric field. So first point, second block, and now the third block, finding the net force. So it will be F12 plus F13. So that's the vector form, but now of course we need to write it in a component. Adding two vectors in a component form, what can be easier than that? Add corresponding components and it's done. So probably I'll write it here. So F1x, of course it will be F12x plus F13x. X component here, X component there. So this is positive, this is negative, so of course components will be subtracted, right? Okay, I'm not going to plug to save time. So the answer will be 1.6 times 10 to the power of minus 5 newtons. So that's the value of the X component. So yeah, the X component of the net vector points actually this way. So my picture is reasonably good, Okay, so now the Y component. F1y equals to F12y plus F13y component. In this case, it's simple because this is 0, right? This component is 0, F12y, right? So this is 0. So the whole contribution comes from this. So I just need to rewrite this. So it will be 2.1 times 10 to the power of minus 5 newtons.
Professor, I have a question. Professor.
Yeah.
So you did a 3.6 minus 2.9. Isn't that 0.6 and not 1.6?
Okay, so far I've trusted my calculations. Okay, let me check. 4.5 minus 2.9.
Oh,
It's
4.5. Oh, okay.
Yeah.
Okay. Yeah, that's true. Okay.
Okay, good.
All
Right. I restored my confidence.
right.
No, it's possible, right? Especially seriously, I don't like crunching numbers, right? I know that you guys love the numbers. I remember one student came to an office hour several years ago, and after discussing using symbols at the end, he said, "Give some numbers. I would feel much better." Right? Yeah, it's a good addiction, but not completely great, right? So you should be comfortable with both, using numbers and solving the problem using symbols. So, of course, I can actually frame this with red, because that's basically the answer, right? Because if you know component of a vector, what else do you want? Of course, you can be picky and you can ask for magnitude and direction. Okay, so let's find the magnitude, for example. Right? But at this point, you can say, I know everything about the final D net force. So, magnitude, now let me put a new bullet. So, magnitude magnitude of F1, right? So it will be, okay, I will write underneath. So F1 equals square root Pythagorean theorem. Okay, I can even maybe redraw the picture because at this point sometimes still some students are confused. All right, so let me just draw only vector F1. All right, so this will be our vector F1, right, F1. And what we just found, we found this component. It's a F1x, right? And this component, F1y. Right. So finding the magnitude of this vector F1, Pythagorean theorem, properties of a right triangle. So square root of this plus square root of that and square root of that sum. Right. Again, based on my experience, sometimes at this point students kind of not comfortable, but once you draw the picture, they of course they all realize, of course I know that. Right. F1x squared plus F1y squared. So numbers are given. Okay, let me look at my values. Okay, so it's a 2.6 times 10 to the power of minus 5 newtons. So that's the strength of this force, right? So that's the force which is going to act on charge Q1 eventually, right? Because you can find direction, you can introduce, for example, this angle phi, let's say. Again, it's up to you which angle to use. And of course, in that, again, once you have a picture like this, most of the students see it. If you use tangent of this angle, it's just the opposite side versus adjacent. Opposite, it's a y component. Adjacent, it's an x component. Just a ratio of those two components. Of course, tangent of phi, okay, force of habit, I wanted to write theta. Phi equals to absolute value of f1y and the absolute value of f1 x. Yeah, opposite versus adjacent side. Yeah, right. Okay, I didn't calculate. You can calculate the phi, right? So I don't know, for whatever reasons I didn't calculate angle phi. Again, we've done similar problem in the past, right? So I just reviewed it, wanted to feel like reviewing it. Then once, a couple of years ago, on the final exam, I decided, instead of giving a problem about finding the net force, I just removed this charge, right? And ask students calculate the electric field, net electric field at that point. And plenty of students, and some of them are quite good students, right? They started panicking. So where's this third charge? What should we do? It's just remove this charge and you will have electric field created by this charge will point that way. Electric field created by this charge will point that way, right? And just add them up, so you'll basically have identical problem. But in that case, of course, the nature of the quantity which you want to find is different, electric field. But the ideology, strategy, everything will be the same. I was, back then, I was kind of surprised that plenty of students were really confused. Okay, so that's what I wanted to tell about this. Again, guys, if you need some additional explanations, tell me, because now I will have to erase every time because I want to keep this in front of us, because we need these formulas, pretty much all of these formulas throughout the whole exam review session. And that will be in a dynamic state all the time, changing. Okay, so if you don't mind, then I will start erasing this slowly. Now, let's talk about electric force. Electric field is given, charge is exposed to the electric field. What about the electric force? So this will be number 2. You know, the more I work from home, right, the more I admire my neighbors, right? They've been so patient with all these noises. Right, so now it's sort of a second part. It consists of several semi-conceptual questions, right? And the big problem will be um, after a few of these semi-conceptual questions. So let's assume this situation, sort of like a pendulum. Let's say this is the ceiling, and here we have charged mass. So it has mass, it has a charge Q. And so pretty much this is the static situation, right? So we exposed this charge to some electric field, right? Some electric field. On purpose, I'm not drawing a direction of this electric field lines, because basically that's my question. And let's assume that this charge is negative. Probably let me erase this and write, so it's a minus Q. Minus Q. Let's assume that this charge is negative. Can you tell me, can you think for a second, what's a direction of these electric field lines? So basically, is the direction of the electric field this way or that way? Left or right? What's the direction of the electric field? What should be a direction of the electric field?
To the left.
In order to have a situation like this, yeah?
Yep, left, I agree. You said to the left.
Left?
Yeah,
Left.
to the left.
Okay, some of you are thinking, okay, let me draw a small vector, right? I don't trust you. All right, no, I'm kidding. So, yeah, let's analyze. First of all, what should be the direction of the electric force? We need to draw all the forces in order to have some, in order to make all the steps and analyze it properly, right? So, of course, there should be a tension force, right? Ft. Of course, there is also gravity this way. And in order to have a static equilibrium, this situation, the system in this position, of course, electric force must point this way, right? So because all these forces, components of these forces in all directions, in x and y direction, must balance each other, right? So of course, electric force must point this way. And since the charge is negative, right? So F equals UE. So basically, I can write it as minus absolute value of the charge times E. So since direction of F to the right, so of course electric field must point to the left, because that minus flips a directions of force relative to the electric field. So you're absolutely correct. The electric field in this case must point to the left, right? So the question was about E direction. Right. Yes, so it must be to the left. So you're absolutely correct. Of course, if this charge were a positive, of course, electric field would be in the opposite direction, to the right. Right. Okay, cool. Right. I just again keep reminding students about with this problem to pay attention to the sign of the charge, because again it's another place for students making silly mistakes. Of course, everyone knows that if charge is negative, we have to carefully flip the direction and so on. But still, sometimes students forget during the exam or a test, right? So, of course, silly mistake. That's why I keep telling you about that. And of course, the more you tell about something, the longer you will remember that. I remember when I was a high school student, right, our teacher in language, right, Ukrainian language, used to ask us almost exactly the same question over and over again, right? We were laughing at her, right? And so what, she's so silly. But now what, 30 years has passed, and that's what I remember. That's the only thing I remember from that course, right? Okay, so next one. Now let's talk about properties of conductors. Right, so pretty much this part. Okay, so it was the first bullet, in this problem number 2. Now let me put the second bullet under the roof of problem number 2. So let's assume that we have this sphere made of metal, conductor, right? Or maybe let's assume it's even electrically neutral. Let's say radius is given and it's a neutral. And of course it's electrically neutral, right? And let me dump a couple of charges, for example, over here, let's say Q1, let's say positive. Here, Q2, let's say again positive, right? And this very simple question, what's the value of the electric field inside of this conductor, inside of the conductor? I'm sure that most of you already know the answer, right? But again, sometimes I still see students struggle a little bit with this. So what happens? Let's just quickly discuss, right? So of course, these 2-point charges, they create their own electric fields. And of course, this electric field penetrates into this conductor, right? Of course, those electrons inside of the conductor, they feel that electric field, start experiencing electric force. And of course, that electric force will start driving those electrons crazy, right? And of course, the electrons, as a result, will start running like crazy, right? In order to do what? In order to create their own internal electric field, of course, with positive charges. So that inside of the conductor, the net electric field would be 0, right? So of course, these electrons will probably, most likely, will come to this side, right? So there will be here some surface charge density, some charge on the surface. Some charge on the surface, right? And of course, they will leave behind positive charges over here, right? Right. So these pluses and minuses, they create internal electric field so that if you add that internal electric field with electric fields created by these point charges, the net electric field inside will be 0, right? It doesn't matter how much of charge you're going to distribute around this sphere, right? Maybe you can put some negative charges here, some positive charges there. These brave electrons, right? They will run to the border like brave soldiers, right, to protect their territory, right? And they will manage to redistribute themselves properly, and sooner or later they will make electric field inside 0. Of course, if you expose this metal to some very, very strong external electric field, yeah, you can damage maybe if electrons cannot handle that. In that case, most likely you will just damage the material. But that's completely different story, different part of physics, damaging material. We're talking about normal amount of electric field strength, right? Okay, so it doesn't matter what you have outside. Electric field inside of the conductor will be 0 if you wait for a short period of time, so that the conductor reaches electrostatic equilibrium. Okay, E is 0. All right, so then I'm thinking, okay, maybe I will, I will write underneath. Now the next one, sort of conceptual questions. No, here we'll have to do some calculations. So let's assume that we have this conductor, right, metal. I usually write metal because I'll have to write less. Conductor is a longer word, right? I'm also conservative system, right? Then there is a hole, right? A void. So basically the metal is over here, right? And let's just dump some amount of charge. In this conductor. So let's say we dump in the conductor some charge. I don't have a particular numbers. I use symbols, right? But you can give me some numbers. Usually in exam review session when we have normal classes like live interactions, right? Usually I bug some students. Give me some number. Give me some number, right? So what's the total amount of charge inside of the conductor, right? Let's give it, I don't know, 5, 7, or -5. Okay, let's say, let me write. So Q total is -7, for example, Coulomb, right? I'm just making it up. Right. Then let's dump a point charge over here in this hole, right? So let's say this is, which way I label it? Just Q. Q equals to, I don't know, what number?
4.
Is 12 good? Oh, we can add make it also negative. I know -12, for example, Coulomb, right? Okay, I just made it up. And so the question is, what's the total amount of charge on the interior surface and exterior surface? Because we remember that excess charges cannot be inside of the conductor. No way, right? So they can be either on the exterior surface or outside surface and inside surface, right? Okay, so first we need to answer the question. Q, which way I label it? In, probably. Okay, let me label just Q inner surface. Okay, this you can answer immediately, right? Of course, if you want, you can prove it like we've done in the lecture, convincing ourselves that the total amount of charge on the inner surface in this case will be equal to the charge, equal in absolute value to the value of the charge inside, but of course with the opposite sign. So if inside we have -12 coulombs, then on this inner surface or interior surface, the total amount of charge must be positive plus 12 coulombs. In simple words, just this negative charge will attract positive charges to the interior surface. Actually, strictly speaking, it's just the electrons will run away, right, inside of the conductor, leaving behind positive charges, because positive charges, you remember, cannot move, right? Of course, distribution of these positive charges on the surface will be complicated, right? It's a different story, and description of that will be complicated. But we can bet all our money that the total amount of positive charge on the interior surface will be equal to -12 coulombs. Right. So this is Q inner, right? Okay. So Q inner surface equals to minus Q inside, which is plus 12 coulombs. Usually I don't ask for a proof on the exam. Usually I ask, okay, just tell me what will be the total amount of charge on the inner surface. Of course, I can make this situation more complicated. I can dump a few point charges inside, right? But in this case, just find the net charge inside of the hole, and on the inner surface there will be that charge, but with the opposite sign. Right? So its idea will be the same. You will have to find at the same time also the net charge inside of the hole. Then, what about the amount of charge on the outer surface, right? So here, Q outer surface or exterior surface. So let's find outer surface. Okay, so now of course you need to run some algebra, simple algebra, which is based on conservation of charge. Conservation of charge inside of the conducting material, inside of this metal. This charge, it's in the void, it's not part of the conducting material. It's in the vacuum over there, right? So this charge is not part of the conducting material. I just want to apply conservation of charge inside of the metal. Right? And we know the total amount of charge we dumped into this conductor, 7 coulombs. Right? So, and we also know that this total charge can be only in 2 places: interior surface and the outer surface or exterior surface. Conservation of charge inside of the conductor. Right, so conservation of charge inside, again, I will emphasize, inside the conducting material. inside, maybe I'll write, yeah, the conducting material did. Some students get confused at this point because before this we applied Gauss's law a lot, right? In order to find Q enclosed, we counted all the charges which were physically present inside of the Gaussian surface. But here we're not counting this Q, but because here we apply conservation of charge. There we applied Gauss's law. So these are two apples and oranges. These are two completely different things. Gauss's law treats charges in its own way, with its own level of cruelty, right? This conservation of charge treats charges in its own way. So in order to apply here conservation of charge inside of the metal, this charge is not inside of the metal, so I'm not counting it. But if we applied the Gauss's law, yeah, I would count the charge if it was inside of the Gaussian surface. There's two different things. We just need to know how to apply this idea or that idea, right? There are no universal rules, right? Okay, so now I can write this, so Q total, because this total charge doesn't run away. I mean, this charge doesn't run away from the conducting material, right? So, and as we just discussed, it can be only on the outer surface and on the inner or interior surface, right? So this we just found. Okay, let me switch to Q capital, right? Or maybe here, let me switch to Q small. Yeah, I just realized that I'm not consistent with symbols, right? So Q inner, right? Okay, now it's better. So we can solve it for this, because this is given, this we found, so we can find Q outer. Q, it's so difficult to write here, so it will be Q total minus Q on the interior surface, right? So now we just need to plug numbers. Total -7 coulombs. Then minus from the formula which basically we derived, but I wouldn't dare to call it derivation, but anyway, nevertheless, right? So a minus, and on the inner surface, what's the inner surface? Plus 12. Okay, so not a big deal. So plus 12 coulombs, right? So it will be minus what? Minus 19, negative 19 coulombs. Minus 19 coulombs. So that's the total amount of charge on this outer surface, right? So it becomes more negative. So we dumped only 7 coulomb charge, but on the exterior surface, the amount of charge more, because why I drew negative, guys? Why you waited, right? You should have started screaming immediately, right? I derived it's a plus 12, right? I kept talking about this, and you waited until I humiliated myself completely, right? Of course, pluses, right? I don't know what I was thinking about, right? Pluses. Now, when I started explaining physics, I realized, damn it, what is that, right? So, of course, since electrons just run away to the outer surface, leaving here positive charges, right? And that's why the amount of charge on the outer surfaces becomes so negative, minus 19, right? Because they run away from this border to protect that border. Right? And again, they keep running basically in order to make electric field inside zero, right? That's their goal, right? Of course, electric field inside is zero. Okay, let me just remind you again. That's why they keep running to this surface or that surface to make electric field zero. All right. Many times I gave a problem like this, similar to this, on the exam. All right. Okay. About fluxes, let me put aside. Maybe then later, if we have time and inspiration, we can discuss that later. Now, let's play with Gauss's law. And let me give you kind of problem with a twist, right? So let me again tell you. So we applied Gauss's law for problems with two types of symmetries: spherical symmetry, cylindrical. So I'm telling you in advance, and I told you already several times, definitely there will be one problem about Gauss's law. So far, after 6 years of teaching this course, right? So almost every first exam had a problem about Gauss's law, and it's either spherical symmetry or cylindrical symmetry. So you just need to train yourself, right? So that you're quite comfortable, right? So here I want to discuss cylindrical symmetry, right? In the lecture, we discuss spherical symmetry. In our recitation classes, we discussed cylindrical symmetry. So just to review everything, right? And of course, there are only several situations: finding electric field inside, outside. Of course, I can make hole inside of the, for example, sphere, right? Dump a charge at the center. But again, finding the flux will be the same. The question is usually about finding properly the enclosed charge. Right. But that's usually just look at the picture, right, and count all the charges, right? Okay, so now, so this was problem number 2, which consisted of several conceptual questions, and now Gauss's law. And then after that, I have markers almost everywhere after almost a year of classes here. And then problems about using energy approach and so on. But for now, it's a number 3. Okay, I need to rewrite this. So number 3. And cylindrical symmetry. Okay, let me tell you immediately. So we have cylindrical symmetry. So there is a infinitely long charged cylinder with a concentric hole, and inside of that concentric hole I will shove another small cylinder with a smaller diameter, right? Okay, so let me draw that. Probably I will start with the outer surface. Right, so no, let me step lower step. Right, so let's say this is my outer surface. Then, you know what, let me turn it slightly. Let me make this wider, because I will have several surfaces and I need to show them all, right? So let me draw it like this. Okay, so it's wider. So as I said, there is a hole. Let me draw it like this. So this is not a metal, it's a charged cylinder filled with charges. So it's not a conducting material. So I can draw this dashed line. Right. Then, as I said, inside of these, let me position another cylinder charged with the same charge density. Okay, let me draw it here inside. All right. And this will be second cylinder. And I can draw another set of dashed lines. Volume charge density the same. Rho given. The same for both. You know, okay, yeah. same for both cylinders. Okay, I can maybe even draw their pluses. So let's say it's positively charged. Plus, 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 plus.
Will rho
plus
always
here.
be the same for both, or just in this specific instance?
No, in this particular case, just a little bit too simple, just to make it a little bit simpler, right? Of course,
Okay.
charge density can be different, right? It just in this case, I decided why not. It's not the major issue if I give you the same or different charge density, right? The major idea of all these problems to see if you are capable of applying Gauss's law, right, properly. Those are peanuts, the rest, right? So here we have, right. So we need to find electric field everywhere. Radii are given, of course, radii are given, and those radii, inner cylinder radii IA. All right, so let me draw that here. So this is A, then here B, and the outer cylinder is C. A, B, C. Okay, so we need to find the electric field. Of course, strictly speaking, everywhere. But finding electric field in this cylinder, in the very core cylinder, right? And outside of that very core cylinder, it's exactly the same problem. That problem, okay, these cases will be exactly the same like the example which we discussed in our recitation classes. Not a single symbol different. It will be exactly the same. So first you will pick the Gaussian surface over there, right? Some small cylinder, right? Calculate Gauss, calculate electric flux. Then in closed charge, you can look at our nodes. I want to look here. I want to calculate electric field in the most complicated parts, in this region and outside. Because inside over here, the problem is exactly the same like the problem discussed in the recitation classes. In our recitation classes, right? So you can review that. I want to look at more difficult situation. So let me label these regions. So the first one is inside, it's 1. In this hole, it's 2. Then in this region, it's 3. And then here, 4. So 4 regions. I want to find electric field in the region 3 and region 4. All right. Okay, so let me start with region, I think for, region 3, which is actually I would consider the most complicated. So region 3, right? So Gauss's law, let me just rewrite it. So integral over the closed surface E dot dA equals to Q enclosed over epsilon naught. I've been writing this Gauss's law so many times. Right. Okay, so first step, of course, as usual, we need to pick a Gaussian surface. Again, any surface you want, but of course that surface must be in the region where you want to find electric field. We want to find electric field in region 3 between what? B and C, right? Between these two surfaces with radius B and radius C. Right? So let me pick that surface. It will be again cylinder over finite length. Right, so it will be here one end and here the second end. Oh, it will be very wide. Right. So something like this. Right. Of a finite length L. L is not given. So that's my Gaussian surface. And of course, of a arbitrary radius R. Right. Okay, let me emphasize that R between R is larger or equal than B and smaller and or equal than C. Okay? And now steps will be identical to the steps which we made in our recitation class. But let me repeat them one more time, right? So this integral E dot dA. So first of all, it's a closed surface, right? This cylinder consists of three surfaces. Cylindrical wall, front facet, back facet. So of course, in order to take this integral, we need to split that surface into three. So let me label that. This surface is S1, this will be S2, and this surface, back facet, is S3. So three surfaces. So we're going to split this integral over the closed surface over the into three integrals over those three open surfaces. So first integral over the surface S1 E dot dA. Then leave some space, right? So stretch these three integrals, because underneath I'm going to write explanations about what happens to this or that integral. So plus integral of E dot dA over S2 and plus integral of E dot dA over the surface S3. So three integrals. At this point, I want to draw electric field vector on the picture and all these dAs. Again, I'm not going to justify now that electric field, direction of the electric field in this case is radial out, right? I justified it in the recitation classes, right? So we just, now I will just say like usually books say. The books usually say, okay, because of the cylindrical symmetry, it's obvious that the electric field is radial and of course point towards the outside. So, all right. But before drawing electric field, let me draw area vector. Right, area vector. So let me pick this patch on the cylindrical wall. Of course, the area vector, you remember by convention, it must point towards the outside. And it must be perpendicular to the surface. So it means that area vector is this, dA. Then for this patch on this side on the surface S2. So this patch belongs to this surface S2, front facet. Or I can use my salt again. I forgot, right? So basically area vector, so this over here I want to draw. So this will be dA for the surface S2. And of course I can do similar for the back facet. Over here I can take a small patch, and of course now dA will point that way, because again all these area vectors by convention must point towards the outside. Okay, so now we see all these dAs. Now let me draw electric field vector. Since it's radial everywhere, so on this patch electric field will point that way. On this patch, okay, now place for plenty of mistakes. So students develop a habit, because very often our area vector and electric field vector kind of parallel to each other quite often, right? But not in this case. But students develop that habit, and here they still draw electric field along area vector. No. Electric field is radial everywhere. It doesn't matter where you are, on this surface, that surface, electric field, direction of the electric field. We cannot change direction of the electric field using our imaginary Gaussian surface. Gaussian surface is an imagination. It cannot change direction of the electric field. So if direction of the electric field is radial everywhere, it must be radial even at this patch. So it means that electric field must point this way. So still radial, all right? Quite often students drew electric field vector in the wrong direction. It's a wishful thinking that with our imagination, with this imaginary surface, Gaussian surface, we can change direction of the electric field, right? It would be too good to be true, right? Right, and the same for this patch, right? Again, electric field still radial. So it means that it must point that way approximately. Okay, I'm trying to draw three-dimensional picture to the best of my ability, right? I didn't go to art school, so that's my best picture. Okay, so now we're all set in order to take care of these integrals. Again, you see, steps are exactly the same like what we've done in our recitation class. The only difference will be when we start counting in closed charge, the only difference. So let's start with this, S3. Let me separate it. So for S3, E is perpendicular to dA. You see, this angle is 90 degrees. So E is perpendicular to dA. So of course, if you write dot product explicitly, so it will be E dA times cosine of 90 degrees, right? Cosine of 90 degrees, 0. So the whole answer is 0. So this integral, as a result, 0. You could have seen it from the very beginning if you just recall the meaning of the electric flux, because what are we calculating? We're calculating electric flux through this back facet. And since electric field is radial, of course, it's parallel to that surface, right? So here's our back facet, right? And the electric field is radial like this, right? It's parallel to this surface and this surface. So if electric field parallel to the surface, of course, physically, electric field cannot cross that surface. It means that number of electric field lines crossing that surface is 0. Flux is 0. Right. Right. So, but we showed it mathematically. Exactly the same story with S2. So exactly the same. I will just write down. So E is still perpendicular to dA, and as a result, this flux is again is 0.
Professor?
Only this. Yeah.
Quick question. Do we need to show this in the exam if we get a question similar to this?
Usually, I ask explicitly to draw these vectors, right? Electric field and area vectors. Then it would be awesome if students sort of explain, but if sometimes I see a student skip, then I have to sit and make a decision. Okay, sometimes okay, oh, why not? Yeah, I can give full credit, right? Right.
Okay, so rather do it and be safe then, I guess.
Of course, it's better to explain everything, right? But
Yeah.
sometimes, but I do demand from students to draw these vectors, because in that case, yeah, it's obviously if vectors perpendicular, that flux will be 0. If they are parallel, right, then it's not 0. Right? That's
Okay,
what I demand.
awesome.
Right? Yeah.
Thank you.
Yeah. Of course, because if I pushed for all explanations from students, right? So then this course will be will be dragged down significantly, right? So I demand for very essential part explanations of the very essential parts. This is also essential, but okay, all right. You ask me a tough question because every time it's a sit and make a decision, sitting and making a decision. Yeah. So now this cylindrical wall. Now obviously they are parallel to each other. E is parallel to dA. And of course, in this case, the angle between them is 0, so it's a E dA, and cosine of 0 degrees, because parallel vectors. What's the angle between two parallel vectors? 0. Cosine of 0 is 1, so it will be just a E times dA, right? Okay, so now we can finally write down the flux. So it will be E dA over the surface S1, right? So now here we have vectors, dot product of two vectors. Now we have just a product of two magnitudes. So now we don't have vectors. Now the next step, using the symmetry, right? And symmetry reasoning. So of course in this integral we are on the cylindrical wall all the time of this Gaussian surface. So if you are over here on this patch, and if you look which charge distribution of charges, if you look at the distribution of charges, which of course create this electric field strength, if you look from this point, and then if you move to different patch on this Gaussian surface, and again, if you look at the distribution of charges which create the electric field at that point, again, distribution of charges will be exactly the same. So it's just an indication that electric field strength will be exactly the same. Strength, not the direction. Direction's of course different, but we have strength over here. Right? So because of the symmetry, we can legitimately say that E is, since electric field is constant, electric field strength, it's a constant, CONST. Okay, it looks like M, but sorry. All right, since electric field is constant, but again, it's only on the Gaussian surface. Because if you step away from the Gaussian surface, of course, electric field strength will be different, but we don't have to step, no, actually not don't have to, we must not step away from the Gaussian surface because we integrate over the Gaussian surface, right? And because we use, we picked it nice, since it's concentric with those cylinders, so we can utilize the symmetry. In the full extent, utilize the symmetry. So if it's a constant, of course, electric field can be extracted, right? So as a result, we're getting E integral of dA over the surface S1. Again, strictly speaking, it's still calculus 3, but we know the answer of this, right? It's basically the surface of this cylindrical wall, right? I'm just trying to cover the brand market basket, right? So how can we find the area of the cylindrical wall? Some students have troubles with that. My explanations are quite simple because everyone remembers how we can find the area of this, for example, page. Okay, let me point this way. It's just A times B. Everyone knows how to find the area of a rectangle. But what's the difference between cylindrical wall and this? You just roll it like this. And now you got a cylindrical surface. Although the area is still the same, we didn't change the area. So it's still, again, A times B, but now B, it's a circumference. So it's just this A times B, which is 2 pi r in this case. So it's that's how you can remember, right? So in this case, it will be 2 pi r times L. L is this length of this Gaussian surface, right? So it will be equal to E times 2 pi r times L. So that's the value of the flux. Okay, and now, of course, we can go back. So we calculated this flux. Now we can equate it to the Q enclosed. So we just need to find Q enclosed. All right, okay, now the trickier part, because here more or less students show some expertise, but the problem, yeah.
Yeah, so just to make sure, so the electric field always points outside, right? Away from the
okay. In the recitation classes, I justified it. It justified it, right? So in this case, you can just remember, right? So for the cylindrical surface, it's radial, right? But again, I just don't want to run the same justification, although I can do it, right? Let me do it. Let me finish this problem, and then after this problem, I can quickly justify why the electric field has a radial direction. Right.
All right.
Mm-hmm.
Okay.
Because I'm running out of space, and I don't want to occupy more space with that justification, right? Okay, because I have only that part left, right, to use. Okay, so Q enclosed, and again, warning you. At this point, I usually ask, okay, in the problem, find Q enclosed, and still after lots of warning from me, still students just solve for Q enclosed this equation. They just write Q enclosed in terms of electric field. It's not wrong, but it's completely useless because we don't know the electric field. That's our goal. We need to find eventual electric field. Writing one unknown in terms of the other unknown, it's not wrong, but again, it's useless. Right. Of course, it means that that question was not answered at all. Pretty much, it means just 0 for that particular question. Right. Okay, so now Q enclosed. That's again, Q enclosed in terms of physics, it's probably the minimum amount of physics. It's just you need to look at the picture and, and count. So let's see where Q enclosed in this case. Again, it's the total charge physically embraced by our Gaussian surface, right? So where that charge is. First of all, the part of this internal cylinder is inside. So let me show it over here. I will use blue, right? So this is, right? So this will be one part of Q enclosed, right? So let me call it Q1, the first part of the total enclosed charge. Agree? Because then there is a hole, there is nothing. Of course, there is no enclosed charge in this hole, right? But between a surface with radius B and radius C, there is a charge. But again, we need to know, we only need to count the charge which is within the surface with radius r small. And r small, you remember, it's over here between B and C. So the second part of the charge is over here, right? In this, okay, let me draw it, but there is something like this. It's here, right? Okay, and I can draw it this and here. So it's this second part of the charge. So this is, let me label it Q2, right? And between them, of course, this hole, which is between surface with radius A and surface with radius B, right? Okay, so now let's count these charges. So Q enclosed, right? Just three-dimensional imagination, right? So Q1, let me write, so Q1 and plus Q2. Q1 here. So how can we find that charge? Volume charge density is given, right? So how can we find, for example, mass of this box with salt if we know mass density? You take that mass density and multiply it by what? By the whole volume of this cylinder, right? So how can we find the volume of the cylinder and volume of this cylinder with radius A, internal cylinder, right? So it's a surface, this surface times the length, volume. How can we find the volume of the cylinder? Base, surface of the base times the height or length. So it's a pi A squared times L and times the density. Density in this case are rho, volume charge density. So Q1 is will be pi. You know what? Probably let me write in this way first. I don't want to write immediately expression. Let me write in this way. So density times the volume with radius A, V sub A. Basically, it means the volume with the radius A. Then, and of course, volume of radius A, I just told you, it's a pi A squared times L. I will write it in the next line. Now, Q2 over here. Again, density is the same, but now we need to use the volume between surfaces with radius r small, that's external radius of our Gaussian surface, minus surface with radius B, that's where charge ends, and then after that there is a hole, So volume, let me write between R and B, basically surfaces with radius R and surface with radius B. Just imagine, right, this situation. It's I wouldn't even call it physics. It's just geometry, right, with densities, right? But again, every time, most of the students struggle with this at this point, where basically, as I said, minimum amount of physics. Okay, so now let's write explicitly. So rho and pi a squared times L. Another place for silly mistakes. Very often I see students use 2 pi r or something else. Okay, now it's a virtual exam. You have everything, right? So you can make sure that you use area, not circumference of a circle, right? Don't make those unnecessary mistakes. So then plus rho and the volume. How can we find that volume? Basically, okay, I couldn't find anything better than this paper roll. Right, so how can we find the volume of this, for example, paper roll, although we know that here there is a hole? So again, we need to take the area, this area, right? So how can we find this area? It's a pi r squared area of this larger cylinder, and then we need to subtract area of that hole. So it's in our case, pi r squared minus pi b squared. Just subtract the whole, and of course multiply by the length, right? So it will be, let me write it. So pi, as I said, first r squared times L minus pi. So it's a volume of the cylinder with this larger radius, and minus volume of the cylinder with a smaller radius, which is b. Pi b squared times L, right? Okay, so pretty much that's the amount of charge. We just need to simplify, factor out. We can factor out r, rho, pi, L, and but that's the expression. That's the answer. So let me just make it look nicer. I can factor out, as I said, rho, pi, then L, right? Because it's everywhere in each term. And what will be inside? A squared plus r squared minus b squared. So that's the total amount of charge enclosed in the Gaussian surface. Again, the major issue, it looks like imagining this situation. And then just rho times volume, that's it, nothing else. Again, it's the minimum amount of physics over here in this part. So logic and simple algebra, but of course need to be applied carefully. Okay, so that's what we need to plug over here, and we're done. So it will be E times 2 pi R times L equals, so I just rewrote the amount of flux, and now Q enclosed, that Q enclosed divided by epsilon naught. So it will be rho pi L divided by epsilon naught, and A squared plus R squared minus B squared. So now let's get rid of some factors which can be cancelled. First L as it should be, then pi goes, and that's it, right? So as a result, we can write down the electric field strength in the region 3 as a function of R equals 2. This 2R goes in the denominator, right? Rho A squared plus R squared minus B squared divided by 2 epsilon naught times R. Right. So variable is in two places, right? So R squared upstairs, it's a variable, and R downstairs, right? Something similar I solved for spherical symmetry in the lecture. Actually, I didn't solve, I just attached my solution. So if there is a sphere with the hole inside, and then inside of that hole we can dump a charge at the center, right? So basically the same idea, right? Just again, the only problem, you just need carefully use rho times V, rho times volume, right? Yes, right now you are completely depressed, right? Right. No, this part, we've done it. Right. Now we just need to repeat it. Right. And. Okay, so definitely there will be a problem about Gauss's law, either cylindrical symmetry, with cylindrical symmetry, or with spherical symmetry. So now you wanted me to justify the justify the fact that the electric field is radial. You know what? I can probably manage to get into this empty space. Right. So let me just cylinder without any holes, because the reasoning will be exactly the same over here, like over there. So let's assume that we have a cylinder. Okay, let me write it. Draw it here, right? So let's say this is our infinitely long cylinder, charged. And let's say we want to find the electric field at this point, let's say completely arbitrary point. And let me draw auxiliary line, which is perpendicular to that cylinder and which goes through the center. And since it's a uniformly charged cylinder, of course I can find, for example, over here, point charge. Why not? It's a uniformly charged cylinder. I can take a small point charge. And of course, contribution to the net electric field at this point from this point charge will be this, E. Right? But at the same time, since it's an infinitely long cylinder, of course I can find symmetrically positioned charge over here. Point charge, the same in the value, right? So of course this charge is going to create its own contribution to this point. It will be something like this. And since these charges are the same, because I can find symmetrically position, these distances are the same, so of course strength of this and strength of that are the same. So if you add them up, you will end up with the electric field, net electric field, in the radial direction all the time. So these horizontal components of these two fields cancel each other all the time. So it doesn't matter. If you take any charge on this side, I can find symmetrically positioned charge on that side, and horizontal components will be cancelled, leaving us only radial direction of the electric field. So that's how I usually justify why electric field is radial all the time. So as a result, now I can draw. So electric field is everywhere radial, right? Something like this. And of course, if you are over here, of course, electric field is still radial. Don't change the direction, because it's a wishful thinking that with the imaginary Gaussian surface you can change direction of the electric field. No, the direction of the electric field will be radial all the time. Okay, but again, if you sort of transpose this problem to spherical symmetry, it will be easier, right? In the spherical symmetry, I can dump a point charge somewhere at the center, right? Calculations of the Q enclosed will be easier. Right? Okay, so that's okay. I'm not going to apply for the finding electric field outside, because this part will be exactly the same, just the total amount of charge. Q enclosed will be slightly different, right? So over here, I think instead of r squared, we will have only c squared. I think that's the only difference. Yeah. So it will be a squared minus b squared plus c squared, right? So the rest will be exactly the same. If you try to find electric field outside of the whole construction, outside of the whole structure. Okay, so this will be included, right? Yeah. So now, so what about the time? So we've been almost 1 hour 45 minutes. Yeah. So now let's play with electric potential energy in the electric potential. That energy approach. Let's solve a couple of problems using energy approach and force approach maybe. Yeah. Okay, let me get some water. Okay, I will start erasing this. Okay, so the next one will be number 4. Okay, I will probably erase. No, I can erase. The right is over there at the end. So, number 4. Okay, a proton and electron. Okay, where are my balls? Right, so a proton is stationary. Maybe it wants to move, but it is being held, right? So, nailed, so it cannot move. Then there is an electron, which flies from infinity. And when this electron is at infinity, the velocity is given, v0. There are no numbers. Right? So we need to find, of course, these two charges, they attract each other, right? And of course, since the proton is stationary, it cannot move, so the electron will be moving that way, accelerating, because the proton attracts it. So velocity of this electron increases, and we need to find the moment or the distance from the proton when the speed of the electron is 2 times v0. Basically, when the speed of the electron is doubled. Okay, now let me draw the situation. So we have a system, proton, which is stationary, let me emphasize, and then an electron. So let me start with the proton. It's, I'm just trying to estimate the amount of space I might need. So this is a proton, and again, stationary. Here, electron. And this is infinity. So this is R initial equals to infinity. Initial position of the electron. Maybe I can even label over here. So this is initial position of the electron. And its velocity at infinity is v0. So, of course, electron is attracted by the proton, so this velocity keeps increasing. So it means it will travel faster and faster and faster. And of course, at a certain distance from the proton, let's say this distance, let's say it's a final position, velocity of this electron will be doubled. It's doubled. So let's say at this point, velocity is 2v0. So we need to find this distance from the proton to the electron when the velocity of the electron is doubled. So now let me show it. So we need to find this distance, right? So r sub f, r final, that's the question mark. And of course, yeah, r initial, I can show that this is basically r initial equals to infinity, right? So let me check what else I need to mention. It looks like, yeah, that's it. So, which approach to use, energy or a force approach. Force approach in this case is not going to work, and I justified in my recitation classes, because in this case, well, look, in this case, force between these two charges, look at the Gauss's law, Coulomb's law. Look at the Coulomb's law. It's inversely proportional to the distance between the charges. And what happens with this distance between charges? It's getting smaller and smaller and smaller. So if force acting on the electron changes with distance, what can you say about acceleration of the electron? It also changes. Acceleration will change as the electron keeps flying. So it means that acceleration, if acceleration is not constant, we cannot use kinematic equations, and that's what we usually used when we use force approach. First, you apply Newton's second law, find acceleration, and then kinematic equations. But in this case, acceleration is not constant, so application of kinematic equations will be just mathematically illegal, right? Of course, yeah, in that case, you will have to integrate second-order differential equation, but that's too much, not for this course. So as a result, what's left? Energy approach. So let's use energy approach. So I will put symbol 2 because that's our sort of second approach. First, we developed force approach, and now this is energy. So, and I know that one of the biggest problem on the exam, of course, for students, and I remember myself, it's which method to use, which approach to use. So now I decided, right, if it's not completely obvious, I usually tell students, okay, use this or that approach, right? Because again, it's sitting and making a decision which way to go. Yeah, it can be painful. Right. Right, so energy approach, which is based on conservation of mechanical energy. So E initial equals to E final, right? So that's the classical beginning of all these problems. And so now let's write explicitly. So everything should come from here if we gave, or if we have enough information in the problem. Right, so of course it will be K initial plus U initial equals to K final plus U final, right? And of course, let me write the formulas, of course, which we need to use. So potential energy, which formula to use? Again, careful. Here another place for some students for completely unnecessary mistake, or it's an indication that student doesn't understand completely, right? So in this case, we have 2-point charges. It means that we need to use this, because sometimes I see students just grab the potential energy for a charge inside of the inside of the capacitor, right? And of course, it's not applicable, right? So of course we need to use this. So potential energy, it's a K Q. Okay, let me write in general, Q1, Q2 over R. So it's in general. And of course, kinetic energy, it's a 1/2 mv squared. Right? So just a reference. So just wrote down the formulas which must be used. And so immediately, what can you say about the potential energy at the initial point? Initial point is at infinity. If, yeah, I see, yeah. If when R goes to infinity, U goes to 0, right? You remember limits in calculus. At this point, I'm sure that you studied limits. Right, so let me write that. U initial equals, which is K Q1. Okay, let me write it. Yeah, let me write with signs. So Q times minus Q, because we have electron and proton. Electron is negatively charged, proton is positively charged. And R initial, which goes to infinity, of course, this is equal to 0. Okay, so now I can simplify. At least I can dump one term. Such a pleasure to dump terms with. It means less writing, less calculations. It's a very pleasant experience from it. So now, where is our unknown? What do we need to find? We need to find this final, R final. And of course, it's in this term, in UF. So that's what that's our unknown, where our unknown. Okay, so now let me write 1 over 2 mv naught squared, so kinetic, then equals to 1 over 2 m. We know that we want to find that distance where the velocity is 2v naught. So basically we know the velocity 2v naught to the power of 2. Okay, and potential energy at the final point. So it's a k q times minus q and divided by r final. And again, be careful, because even now we use Coulomb's law more often, and very often I kind of force of habit, I want to write the power of 2 next to r. So control yourself, because very often I feel like I want to write that down. Right, so let's see where is unknown. This is our unknown. The rest is given. Mass, which mass? Okay, it's very important, right? We're describing motion of what?
The electron.
Electron. Proton is stationary. Basically, proton that exerts the force on the electron, and an electron is flying. So basically, we're describing the motion of an electron, right? So probably I need to write that mass of an electron, not a proton. Proton, stationary, right? It's not moving, right? So let me write here over here. So mass, it's a mass of an electron, of the electron. Although their own mass is all the same, right? Okay, right. So given RF unknown. One equation, one unknown. Now just needs to be solved for that. Oh, so how should I do that? Probably first I will move this term to that side with plus, right? Right. KQ squared over RF minus, I move the term to this side with plus. So then this stays over there with plus, so it's a m over 2 4 v naught squared, it's this term, right? And this term must be moved to that side with minus. So minus m over 2 v naught squared. Again, be careful with algebra. It's not calculus, it's algebra. Because again, sometimes I see very unnecessary mistakes with moving terms around. So, of course, it will be what? 3 over 2 mv naught squared, right? So if you subtract these two terms, right, you will get that. So now what? We need to free this RF from this. Oh, okay, I can solve it immediately, right? So I'm sure that you also can do that, right? So RF RF equals 2. So it goes to this side, then 2 goes up here, 2k q squared divided by 3 mv naught to the power of 2. Okay, at this point you should be able just to apply whatever method you want. Right. Solving for RF. So let me check. 2, 3, yeah. Okay, yeah, correct. So that's the answer. Again, in this case, the force approach will be significantly more complicated. No, I didn't give numbers, right? And sometimes I do it on purpose, kind of forcing you to practice dealing with symbols, because I know from after high schools, you guys like numbers, but you need to not get rid of that habit, but also must be comfortable with working with symbols. Right, okay, so now next probably conceptual, since we're talking about two-point charges, and then another problem about energy approach, but that time we will play with the capacitor and the charge. But for now, let me discuss another conceptual question. And what about time? 2, yeah, probably like 2.5, maybe we'll get closer to 3 hours, right? So it's normal exam review sessions, right? Final exam can be up to 4.5 hours. We had that in the past. Okay, You know what, I can squeeze it here also without erasing that problem. All right, so let me just draw this line and small bullet, conceptual question. Okay, my neighbors are trying to turn some music, right? So I hope you're not going to hear that. Okay, so we have this situation. There is a point charge, positive point charge, Q capital, stationary. Again, maybe it wants to move, but we're not going to allow that. So it will be, it's basically it's nailed, right? Then there is what? Electron. Yeah, an electron. So first that electron is here, and then it will travel over there. So this is initial position, and this will be the final position of an electron. So it travels along that trajectory. So we need to answer the question, what happens to the potential energy? Similar, but slightly easier in terms of geometry, I asked in the lecture, like 2 or 3 lectures ago, right? And I remember there were, most of you picked the wrong answer, right? And of course I expected that. All right, so what happens to the potential energy? All right. 2U. Right. Okay. 2-point charges, electron and this positive charge. So of course we have to use again this formula, K, Q over R. So U equals K. Let me use. Okay, let me write first in general. Right. And now for our case. For our case, it will be what?
Sorry, Professor.
Yeah.
What does that say after conservation? Can't quite read that. Just top left-hand corner of this.
Okay.
It says
conceptual question.
Oh.
Sometimes I just pronounce assuming that you are at that moment with me immediately, but of course you're lagging behind slightly, of course, because you're trying to write, also understand. So of course, yeah. And I kind of feel sometimes sloppy, all right, in terms of writing. Conceptual question. Okay. Cons quest. All right, so let's write explicitly for our case. This charge is negative, this charge is positive, so it will be K, Q capital, and minus Q divided by R. So immediately we can say what about the potential energy? That the potential energy in this case is negative. And we need to remember that. So U is negative, right? Okay, essential first part of information. Now let's see what happens with this potential energy. So what's dynamics? We know it's negative, but now R, what happens with R? So here, R initial. This is R final. Obviously, R increases as the electron flies. R goes up, increases. Right? But at the same time, R is downstairs in the denominator. So it means that what happens with the potential energy, absolute value. Okay, let me write absolute value of the potential energy. Right now, I just want to see what happens with numbers. And since R is downstairs and it increases, of course, potential energy, absolute value becomes smaller. So absolute value decreases. But potential energy at the same time is negative. So, absolute value decreases, it means what? Potential energy becomes less and less and less negative. It means potential energy increases, right? Out of 2 negative numbers, larger that one, which is less negative, right? So potential energy in this case increases. increases, becomes less negative, right? All right, so U becomes less negative. So we can say potential energy increases. Right? So so we can write finally U increases. Again, here I had an absolute value, and here just U. So it becomes less negative. It means it increases. So a question like this I gave several times on one of the exams, right? Again, logic is not that complicated, but you just need to put together three things. What happens, what potential energy, positive and negative, then what happens with the absolute value, and then adjust it if it's positive or negative, right? Usually after a couple of analysis like this, most of students do well on the exam about this particular question. Of course, I can change, for example, 2 negative charges or 2 positive charges, right? But logic exactly the same. Not exactly similar. Logic is similar. Okay, so now after this, let's look probably the last big problem, and after that one conceptual question, additional conceptual question, and I will call it a day. Should be enough. Right? Okay, I need to erase that. Start erasing this. So it will be number 5 problem. All right, 5. Okay, so before this conceptual question, we discussed this situation of 2-point charges, and now for practice, let's look at the point charge exposed to the uniform electric field created by a capacitor, a PP capacitor, a parallel plate capacitor. So, what is given? First, let me write the system. So we have an electron. So electron, electron inside of a parallel plate capacitor. Again, before we had 2-point charges, now charge in a capacitor. And so, what's the story? Okay, probably I will start drawing it. So we're going to shoot an electron from a positively charged plate. We have to shoot, otherwise by itself electron is not going to travel from the positively charged object because it will be attracted, right? So we shoot it, and we need to calculate the amount of speed that we have to provide to the electron, so that electron will just reach the negative electrode and stop. Just before the negative electrode, it will stop. We just need to find that amount of velocity. Just before it, at the moment when it was about to hit the negative electrode, it will stop. Right? Okay, so now, so that's physical situation, and now let me draw it and show all the details. So we have this is negative electrode. Let's say this is positive. No, that is positive. This is negative. All right. So this is negative, minus, 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 and positive, right? So plus, 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 plus. Of course, yeah, I can draw electric field lines. I like drawing them because then picture looks better. there is a connection between these two plates, right? Aesthetically better. All right, so then, as I said, we have an electron, and we shoot it from the positively charged electrode. And of course, we must shoot it. Otherwise, of course, it will never leave it by itself because it's attracted to the positive charge, right? So it will, probably I need to show this different colors. So this will be, I will label it V sub I. Yeah. So we need to find this V sub I so that it will travel, and this is final point. Let me emphasize. So this is final point, this is initial point, and at this point, V final equals to 0. That's what we want. We want to find initial velocity so that it will barely reach the negative electrode. Then, what else is given? Potential okay, let me write. So of course Vf equals 0, and then potential difference is given. Potential difference is 10 kilovolts positive. It means what? Since it's positive, it means it's a V plus minus V minus, because the potential the positively charged object is higher, or because it's positive, and potential, of course, around the negatively charged object is negative, right? So of course I can write it. So V plus, it just means the potential at the positive electrode, and of course minus V minus, and that's equal to 10 kilovolts. Okay, I emphasize that it's a V plus minus V minus because you will see at a certain point we will need that minus. There will be some point where we will have to expose that. Okay, so now we're going to use two approaches, energy and force approach. In this case, both of them, I don't know which one is easier. Equally good. So let me check if I mention everything. You know what? Let me show the coordinate system. Yeah. Right. And coordinate system, you remember all the time we measure SS from the negative electrode, right? So let me show. This is S, this is 0, and this is D. All right. And D is also given. That's what I forgot to give you. D is 1 centimeter. Wow, it's a big gap, 1 centimeter. Okay, why not 1 centimeter? Of course, at a certain point, you will have to convert it to meters. So 10 to the power of minus 2. Immediately, it's better to convert so that later on you wouldn't forget to do it. It happens. When you get closer to the end of the problem, you get excited and you can start making silly mistakes. Right? My own experience. All right, and yeah, that's it. So now, probably I should show that this is, of course, potential at this point is V minus, potential at this is V plus, and of course, this is delta V. Right, okay, so now I showed everything. So now let's start with the second approach, energy one. As I said, both of them are equally pleasant to solve this problem. Okay, again, total mechanical energy at the initial point must be equal to the total mechanical energy at the final point. Again, why we use those points? Because some information is given at that point and some information needs to be found at that point. So of course it makes sense to use those points to compare energies. So E initial equals to E final. And now let's just reveal all those, all the information in this equation, right? So, okay, let me write, so K initial plus U initial equals to K final plus U final. Right, and probably I should write explicitly which formula I'm planning to use. So U equals charge inside of the capacitor, of course, now this QES. And since S is present, so that's why I showed coordinate system and direction of S, because when we derived this formula, S was measured from the negative electrode. So we have to be careful and measure S in the correct way. So QES, so that's what, of course, we will have to use. You know what? Actually, do we actually need S in these calculations? Just now I started looking at the problem. We have information about the electric potential. So it means that we don't have to dive that deep. We can go to a slightly higher level and we can use this U equals QV because information about the electric potential is given already. So there is no point of diving that deep and reveal all that internal parts. So this should be enough because delta V is given. So I'll take it back, right? So I will erase it. So now we don't need this much of information. So Q times V, right? Okay. So this level, that's what we need. So then let's.
Professor?
Yeah.
But you could use either or, right? Like it wouldn't necessarily matter if you used the one
If you
potential
use
energy
S, then
over the other.
if you're talking about S,
Yeah.
in that case, if you'll try to use S, you will have to find that S, and probably, I guess, yeah, it should be, you should be able to do it, right? D is given, S here 0, there 0, there D. Yeah, you can do it, but I think in that case you will have to make some additional steps because
Gotcha.
you will have to find electric field. Right now, electric field is not given, right? But here you need to know the value of the electric field, right? So yeah, you will be able to solve the problem, but with one additional step, extra step relative to the method if you use just QV, right? So what I started to write, it wasn't wrong. It's just slightly longer approach. Right?
Okay, awesome. Thank you.
Yeah. Yeah, I came to the point of that pleasant feeling of dumping terms, right? So what can be dumped? Final velocity is 0, we know, right? So it means that final kinetic energy must be is 0, not must be, is 0. That's what we want to achieve, actually. Yeah, that's what should I say? That's what we want to achieve. So we need to impose that in our equation, our desires, right? Anything else? No, it looks like, yeah, the rest we need. And also I need to see where is our unknown. We need to find initial velocity. Initial velocity is inside of K initial, basically. That's our unknown. So let me keep it on the left-hand side and the rest of the terms dump on the right-hand side, right? We need to isolate our unknown, right? So basically unknown is here, right? So, okay, I will write underneath. So it will be K initial, it's a 1 over 2 mv initial squared. I'm just rewriting. This term goes to that side, U initial. So it will be U final minus U initial. And of course, now we need to use that QV. So, of course, Q I can factor out immediately, right? Because Q will be exactly the same for both of these terms. So I can write QV final minus V initial. And now look what is V final and what is V initial in terms of that V plus and V minus, because now we need to write correctly that 10 kilovolts. Will it go there with plus or minus? So V final, final point, it's a here next to the negative electrode. So it's a V minus. So this is basically V minus and this is V plus, because electron travels from this point, initial point, which is next to the positive electrode. So this is V plus, right? So I can write, so it's a Q, V minus minus V plus. So you see, But what is given? V plus minus V minus 10 kilovolts. So we need to write it with minus over here, the minus 10 kilovolts. Right? Or I can write just minus delta V, because delta V is given, so I can write it. So this is minus delta V. Right, so it's a minus 10 kilovolts. So that's why I was careful. V plus minus V minus, or V minus minus V plus, because we needed that minus. And also, electron is negatively charged. So let's reveal that minus as well. Right. So let me rewrite it one more time. 1 over 2 mv initial squared equals minus q. Just reveal the minus in front of the negative sign of the electron. And minus delta V. Of course, it will be just Q, absolute value, times delta V. Right. Okay, so basically we're almost done. So now let's solve it for V sub E. Wait, V sub I, V sub I. And, so V sub I equals square root of 2 Q delta V and divided by M. All right, yeah, that's correct. That's the algebraic expression. Of course, numbers are given. Charge of an electron, delta V 10 kilovolts, and mass of an electron, of course, right? So if you plug numbers, did I do it? Oh, no, I didn't. Typical, right? Okay, you can calculate, right? I should have done it. The only thing which surprises me, information about the spacing between plates is given, but we didn't need it to solve it. Of course, you would need it. You will need it if you try to use QES, right? Most likely, I think, in order to find electric field, you would have to use that spacing. But otherwise, it's a completely redundant piece of information, right? I would probably be able to justify if, for example, area of the plates were given. In that case, if area of the plates is significantly larger than the spacing, we can justify, yeah, it's a nice parallel plate capacitor. So we can use all those formulas. Otherwise, now it's a completely, it's not wrong. It's just usually if a problem properly stated, any redundant information, not necessary information shouldn't be there. Right? But again, it's not a crime. Right? So now the second approach, force one, let's use it. I mean, let's practice it because we've done it. Yeah, almost at the beginning of the semester. Now let's apply it for this this problem. All right, so now I will put 1 and write force approach. And you know what? Now I realize why D was given. So because now, yeah, if I now for a force approach, I will have to use D in order to find electric field, right? So actually, in this case, energy approach is more efficient because one number is not needed, right? Okay, so let me sort of write a skeleton of the solution, all right? Like I've done in a few problems, right? And then we will just fill out those again. So we need to find at the end one of the kinematic parameters, V initial, all right? And every time before we find one of any kinematic parameter, like position, travel, time of travel, or velocity, or every time before finding that, we need to know acceleration, because acceleration is the essential part in any kinematic equations, right? Then, in order to find acceleration, of course, we need to know the force. and then we can use Newton's second law in order to find acceleration from the force, right? So now the step before this, of course, it will be F. Of course, let me also right, so over here we'll have to apply Newton's second law. Here, kinematic equations, right? So basically, I'm writing underneath bridges that we have to take in order to jump from that point to that point. Then, okay, of course, it's electric force, right? Then, in order to find electric force, of course, we need to know information about the electric field, right? And of course, in order to complete this step, of course, we'll have to use QE, this, right? F equals QE. And now, like some of you asked me, can we use the approach which first I tried to use in order to find the electric field? We need to find electric field from the information about delta V. Of course, using the spacing between the electrodes. So from delta V, we should be able to find E, and then so on. So that's basically the problem, solution of the problem. Solution of the problem. Right. So now we just need to cover all these steps properly. Okay, so now, of course, from the beginning. So find the electric field. So you remember when we introduced the expression for the electric potential inside of the capacitor, ES, so we immediately at that point we wrote down the expression for the potential difference, which is the voltage potential difference between the electrodes. Electric potential at the negative electrode is 0. Electric potential at this electrode is E times D. So delta V is E times D. So delta V equals to E times D. So that allows us to find the electric field immediately without any sweat. Right. So will be electric field equals delta V divided by D. Okay, I'm not plugging numbers for now. I just want to collect everything, so that derive the final expression, and then only then I will plug numbers. So completed the first step. Now we are here. Now we need to use QE in order to find the electric force. So now electric force equals Q times E. Right? And you know what? Since it's a force approach and directions are important, right? So sometimes some of the directions are positive. Like when we get to the kinematic equations, even acceleration, if an acceleration is a negative, we must put their negative value. So let me write electric field in a vector form. I jumped too fast, right? So let me write in a vector form so that we wouldn't lose any minuses. So electric field as a vector. Look, electric field that way, to the right, you see, electric field to the right, but our S direction is to the left. So strictly speaking, our electric field vector is a negative vector. So let me write that. Absolute value is this, but direction is a negative S direction. So, so equals to delta V over D, and in minus I hat direction. I use I hat as a unit vector for the S direction. I still don't know why Knight used S instead of X, but again, it's not a crime. Okay, and now let me write it in a vector form, QE. And, yeah, so we need to force, so we can just plug it in. And it's an electron. Again, let me reveal the minus. Let me show that minus explicitly. So it will be minus Q. And electric field is also negative. Delta V over D in the minus I hat direction. So I just wanted to get this minus and that minus. It means they balance each other out, giving us force pointing in the positive X direction. And it makes sense because these electron pointing in the positive X direction, it's that way because my S direction that way. So force that way, decelerating electron, as it should be, right? We knew it conceptually from the very beginning. So now we got it mathematically, right? So it will be absolute value of charge times delta V divided by d, and in the I hat direction, and I will put probably plus emphasize, so it's a positive S direction, so to the left. Maybe I'll emphasize, so it's a to the left, to the left, left that way. Okay, so now we are at this point. Now acceleration, piece of cake, because our mass is positive all the time, so direction of the force gives us direction of acceleration all the time. So now acceleration equals force, of course, electric force divided by m. Right, so basically I just need to add m in the denominator of that expression. So q times delta v divided by m times d, and in a plus I hat direction. So acceleration is positive. So, and again, it makes sense because, again, positive direction that way, acceleration that way, basically it means that charge is decelerating, right? Okay, so it means that we can use kinematic equation with the positive value of the acceleration. So we just need to, we can just grab this and shove it in the kinematic equation. So now, and again, let me emphasize, since acceleration is constant, okay, again, I'm sloppy in terms of writing constant. So it means we can use kinematic equations. It's legitimate to use kinematic equations. And which kinematic equation can we use? Actually, we can use any of those, right? It's just a question of reducing number of steps that you have to make in order to find the answer. And logic is, look, equation for x and equation for v have time. We don't have any information about the time. And the question, again, is not about finding time. So it's a clear indication that the equation number 3 would be the most efficient. That equation, which I usually call no time equation, because the major feature of that equation that time is absent. Okay, so now kinematic equation. Let me write that equation. So it's a v final squared equals to v initial squared plus 2 a, right? Acceleration is positive, so I'm writing plus. If acceleration were negative, of course, I would plug minus. And what? S final minus S initial. Instead of x's, we have s's now, right? Okay, so now, of course, we can simplify that. Again, the most pleasant experience of getting rid of terms. Final velocity is 0. Then final position, you see it travels that way. Final position is where s equals 0. So final position is 0. Initial position is here. Initial position is d, because you remember s, I pointed from minus to plus to the left. So this is d. Okay, so now I need to move somewhere. Probably I'll move to there, to this side. So v initial goes to that side. Okay, I can just move this this term 2a minus d, minus 2ad to that side with plus. Right, so it will be v initial squared equals to 2 a times d. Right. So now let me take a square root and plug acceleration into the final expression. So it will be v initial equals to square root of 2 a q delta v times m times d. All right, so it will be q delta v and md, m times d, and times, oh, actually it's nice. Even this approach, in this approach, d is not needed. Phew. Now I feel better, because when I started looking at the second approach, kind of strange. How come that in one approach you don't need d, in the second you need d? Right? It's it would be something really finicky, right? Now, yeah, it's better, right? So d can be cancelled, so d is not needed. So it's even worse. The problem is not stated properly, right? So as a result, it will be 2 absolute value of the charge times delta V and divided by M. What did we get in the first approach? Exactly the same. Yeah, makes sense. Awesome. So this and that. So the same. So probably I would say first approach probably easier because you just start from there and then just start revealing, and everything appears naturally. But here you need to sort of manually put together. So we need to get this, then there, then it's a little bit bumpy. This solution is a little bit more bumpy. That is sort of like a smooth flowing down the river, right? Okay, at least I got some feelings about this and that approach, right? Okay, so 2.5 hours. Okay, slightly more. Okay, the last piece, conceptual, right? So, and after this, we'll call it a day. Right? It's enough. Torturing. Probably I will just use that bottom. I will erase over here. I just want to find electric field conceptually. Information about the electric field, direction of the electric field, and the value of the electric potential at the same point. And some distribution of charges, right? Because what in the previous lecture when I asked, when we were finding a direction of the electric field, information about the electric potential, some students are asking questions in the chat. So how come that electric field that way or this way? All right, after class I read it and I realized, okay, we need to spend a little bit more time looking at that. Why I kind of was a little bit faster and discussing that question, because we discussed direction of the electric field many times in the past, right? So I felt like that is under your belt already, right? But looks like we need to talk about that more. So next, conceptual question. I will put a small bullet. Concept question. All right. So let's imagine that we have some kind of rectangle, or not a rectangle, square, a square. So it will be our first part, right? Yeah. Okay, it doesn't look square. Still good enough. All right, so it's a square, right? If that Malevich's square, black square, you remember painting, right? Famous, world famous painting, right? Which is considered a piece of art. If that was accepted as a piece of art, this square should be accepted as a nice example to discuss this problem, right?
I'm glad you labeled
Yeah,
that. I almost thought that was a circle.
Right. Yeah, modern art is quite interesting, right? It's like I watched one documentary in South Africa. There is a pig which kind of drawing, right? So basically they train it, they put a few buckets with painting, right? Give a brush, right? And by moving head, that pig paints or creates art. And they give that pig a name, Picasso. Pig and like a Picasso, right? Combined Picasso. And they managed to sell those paintings like for several $1,000s per piece, right? Yeah, nice.
Yeah,
Nice business.
I'm actually from South Africa, Professor, so I can definitely tell you that that is true.
So it's a famous celebrity, right?
Yeah.
South Africa.
It's
Okay, I was
pretty
surprised. I
weird,
watched
right?
some travel show and I was surprised to see that. But, okay, as long as it works, right? As long as it brings financial stability to the company, right? To the farm, actually, not the company. So plus Q. So let's assume that we have a positive charge and we have a negative charge over here at these corners of the square. All right, and the question is, we need to find information about the electric field and the electric potential at the center of that square. At the center of that square. And let's assume what is given in order to simplify, because yeah, you can easily find distances if, for example, sides are given. So let me give you this. So this L is given, L, right, and that is also L. So the distance from the corner to the center is L, right? And just because that's not, geometry is not the problem which I want to discuss. Right? Okay, so we need to find the electric direction of the electric field at the center, and information about the electric potential at the center of the square. So let's start with the electric field. Okay, because that's what some students struggle with in the class. So in order to find the direction of the electric field, you can sort of use, I cannot say two approaches, but because it's basically potato, but let's say two approaches. You can first think in terms of a probe charge. A probe charge must be positive, period. Everyone in the world uses that convention. So imagine that if you have a positive probe charge over there, what does this charge is going to do to that positive probe charge? Of course, it will repel it. It means the direction of the electric field, force, and the field will be that way. It's one way of getting the direction of the electric field. Okay, let me draw it immediately, right? So this will be direction of the electric field created by the positive charge. Let's call it E plus. But, or you can think it in this way. Since any positive charge, okay, think about electric field lines, right? You remember electric field lines, they start on positive charges and either go to infinity or ends on the negative charges. So it means that since here we don't have a negative charge, of course, it will go this way, right? So effectively, in our case, we're dealing with this electric field line. So this electric field, just electric field line is over here. So that's the direction. Either imagine a positive probe charge or recall directions of electric field lines. Either approach, of course, is going to give you a correct direction. Right? Okay, so now let's do the same with the negative charge. So negative charge, of course, is going to attract. It's going to attract the positive probe charge, right? So this negative charge, of course, is going to attract the positive charge. It means that direction of the electric field created by the negative charge is going to be this way, E minus. Right? Or think about the electric field lines, negative charge, electric field lines created by the negative charge are like this, right? And we're talking about basically this, right? This electric field line. So this point charge over there, and this is the one of those electric field lines giving us direction of the electric field. Okay, and of course, in magnitude, this field and that field equal because distances are the same, and this charge plus Q and that minus Q and absolute value the same. So magnitude of these two fields are the same. So it means that if you add them up, the electric field direction will be pure horizontal to the right. Okay, so now let me add them up. So this will be E, direction of the net electric field. Questions like this often I gave in the past among multiple choice questions. At some point, final exam, exam number 1, not exam number 2, and for the exam 2 we have other stuff. But on the final exam or the first exam, yeah, quite often. Okay, so direction of the electric field. Now what about electric potential? V. Electric potential. Again, you remember the same electrical aura can be described either electric field or electric potential. Right, so now electric potential, and since potential is the scalar quantity, so we cannot draw any directions, just a bunch of numbers, right? So we just need to write V equals, so it will be contribution, of course, from the positive charge plus contribution from the negative charge, V plus plus V minus. And of course, the second term will be negative, obviously, right? Okay, point charges. We have an expression for the electric potential created by the point charge here. K, Q divided by the distance from the charge to the point where you want to find the value of the electric potential, right? Okay, so let's do it. So this will be K Q over L. Again, I assume that L is the distance from the corner to the center of the square. Again, because I just don't want to spend time doing geometry using Pythagorean theorem. Right, and then plus K, charge is negative, divided by L. Contributions are the same, but opposite in sign. Of course, they're going to evaporate each other, right? So giving us 0. Let me check. Yeah, it was 0. Annihilate each other, probably it's better, giving us 0. So it's a first. Now let's do similar, but for example, with 2 negative charges. Because usually students less comfortable with negative charges, right? Okay, so let me separate this. And the second, again, let me draw my modern art square. So it will be good enough. Let me draw diagonal lines. Diagonals just, and 2 negative charges I will position at those corners are here. Minus Q, and here minus Q. And the same question, what can we say about the electric field direction at the center and the electric potential? So again, let's start with the electric field. The same approach, either think about the probe charge, positive probe charge. So if you position positive probe charge, of course, that probe charge will be attracted to this charge. Or in terms of electric field lines, we will have to talk, yeah, it's about this electric field line. So giving us direction towards negative charge. And the same story with the second negative charge. In terms of probe charge, positive probe charge will be attracted, and direction of the force give us direction of the electric field after canceling the value of the probe charge. And so, and again, in strength of these two fields, exactly the same. Of course, directions are different. Vectors are not the same. I'm talking about the strength, magnitude of the electric field. Okay, so now if you add them up, you will end up with the same direction, actually, pure horizontal. So this will be E. And, okay, the last piece of this exam review session, let's find the electric field, potential, electric potential, net electric potential at the center. So V, after 2.5 hours of yapping, right, kind of brain stops working properly. All right, so it will be, let's add V1 plus V2, because now since they're both negative, I cannot label them V plus and V minus, just label V1, V2. Okay, so now obviously the contributions are not going to cancel each other because they're both negative. So it will be K minus Q over L plus K minus Q over L. So it will be just minus 2 KQ over L. So potential is going to be negative. So it will be minus 2 KQ over L. Right. Again, that Q is the absolute value of the charge because I showed minus explicitly. Okay, so you see it's not that bad. On the exam, most of students answer this type of questions properly. Whew, enough. Almost 3 hours. Yeah, that's pretty much normal.